Welcome to this short introduction to optical flow. Optical flow is the apparent motion of objects, surfaces, or pixels in images. Optical flow is estimated by looking into images in a sequence. Pixels in an image at time t are compared with nearby pixels with the same intensity in an image at time t plus 1. From this, optical flow vectors are generated, which tell us in which direction the pixels are moving. In a bigger perspective, these motion fields illustrate the magnitude and direction of objects of interest, for example moving vehicles. Based on this mindset, the brightness constancy constraint equation is formulated. This equation is essential for optical flow methods. The equation is written as a change of image intensity in x direction times u, plus change of intensity in y direction times v, plus change of intensity over time. This should be equal to 0. U and V are respectively the optical flow in x and y direction. The horn and shank method is a global approach to determining optical flow. This method is about minimizing some error. The total error consists of two parts. The first one is related to the brightness constancy constraint equation, where it is squared and summed up over the whole image. The second part of the total error is related to the change of optical flow in x and y direction. This is called the smoothness error. The change of the optical flow components, u and v, in x and y direction are squared and summed up over the whole image. This error indicates how smooth the change of the optical flow vector is. The horn and shank method should find the optical flow vector uv that minimizes the total error E equal to E sub s plus k times E sub c. The figures show a circle that rotates clockwise. Figure A and B represent the circle at time t and t plus 1 respectively. And by using optical flow algorithms, the motion field of the rotation can be calculated, as shown in figure C. Worth noticing is that the angular velocity is largest at the edge of the circle and decreases towards the center of it as expected. The length of the vectors illustrate the magnitude. Optical flow is used extensively for different objectives, among other things in traffic analysis. In this picture, it is used to distinguish the moving vehicles from the static background and track them. The surveillance camera can then determine features of the objects detected, such as type, number, and speed, if given spatial information. It is also integrated in different kinds of autonomous vehicles for control and tracking purposes. UAVs can use optical flow for tracking, positioning, and navigation.